Okay, let's take a look at this problem. So, in this problem, what we are saying is we have an op-amp or uh, a, a, a op-amp making an amplifier, right? So, we have an amplifier, and let me just draw the amplifier as a black box. And this amplifier is made with an op-amp which has a noise associated with it. And we can model the noise as a external noise, and let's assume that this amplifier is an ideal amplifier, and the noise source has an amplitude of 2.5 nanovolts per root hertz. Okay, now the gain of this amplifier, we have been told, is 40 dB. Now if you want to convert that into normal gain, so 20 log 10 gain in normal terms is equal to 40 dB. So that's how you convert gains into dB, right? And if you evaluate this, what you would get is G equal to 100. So the gain of our amplifier here is 100, and the output that you're getting here is 1 volt. So that's the signal output. Now what we want to find out is what's the RMS value of the noise output here. We don't know that. We have an input noise. We have, of course, an input as well, and we don't need to know what that is, but that input is causing this 1 volt signal. Now we want to know what is this VNO RMS. Okay. Now, of course, the first thing that we can say here is VNO RMS, or let me not write it as VNO RMS, but maybe just class VO here. Okay, so VO is the output amp, the RMS value here is going to be 2.5 nanovolts per root hertz multiplied by the gain, that's 100, which is equal to 250 nanovolts per root hertz. But of course, the reason why I didn't write this as VNO RMS is because what we have also been told is that the amplifier amplifies signals from 20 hertz to 20 kilohertz. It's not all the frequency range. So we need to make sure that we account for the noise only in that frequency range. Okay, so this noise is only between, so it's from, let's say, 20 hertz to 20 kilohertz. Only this noise is amplified, right? All the rest of the noise is not amplified. So what is the noise power then in that particular band? The noise power is basically going to be integration of 20 hertz to 20 kilohertz. Okay, and what is the noise? 250 nanovolt per root hertz. That's the power, the noise power, df. Now if you do this integration, you can find out what the noise is going to be, but that is going to be the noise power at the output, right? That's going to be VNO RMS square. So what is VNO RMS going to be? I'm sure you can do the calculations, and if you do the calculations, what you get is it is equal to 35 35.34 microvolts per root hertz. So that becomes oh, actually, wait a minute, not per root hertz. There's no per root hertz here. So 35.34 microvolts. That becomes the output RMS noise. So now you have the output RMS noise, you have the signal voltage, and therefore what you can do is you can find the SNR, right? So what is the SNR going to be? Let's say you want to find the SNR in dB, and because we have the RMS voltages, let's say it's 20 log 10, and let's assume that this 1 volt that is given is an RMS voltage of the signal. So you have 1 volt divided by 35.34 microvolts. And what does the SNR turn out to be? It is 89 0.1 dB. Okay, so that's what the SNR of the system is going to be.